So let's think about some iodine 131. Every substance has a different gamma, because every substance has a different amount of rate of radioactive decay. So I'll just tell you that the gamma for iodine 131 is 0.086. First of all, how would you interpret this? What does this lambda tell us in words?
So the percent of decay per second. So in this case, 0.86% per second.
That's right. Although actually, I didn't give you the units. I should have said this is actually per day. So what this means is 8.6% of the iodine decays per day. This is telling us that 8.6% of the iodine is decaying per day here. So here's a common type of question. How long will it take for the radioactivity to fall to 1/3? Its original level.
So I would use that's when it's A equals A, not right, because you're talking about activity.
It's like we can go through this together because we haven't seen any examples, but there may be ideas about how to start on this.
So we know that A is going to be, so you find A naught first.
Let's think about that. What would be a good equation to relate A and A naught? If we want the radioactivity to fall to 1/3 of its original level, does that mean that A is 1/3 of A naught, or that A naught should be 1/3 of A?
A should be 1/3 of A naught.
Right. It's probably a good idea to try to build this into our table here. So what we're trying to do in our table is we're trying to figure out, let's see, what would be 1/3 here? About here? If the radioactivity started at this level, we want to know how long it takes for the radioactivity to get to this level.
Right.
So we want the actual radioactivity to have fallen to 1/3 of the original level.
Right.
So putting into our equation here, that would mean 1/3 A naught equals A naught e to the negative lambda t. So instead of plugging in A, we can plug in 1/3 of A naught. And now, what's the first thing we can do to simplify this equation? Oh, one thing we can do is plug in for lambda. So I should have plugged in 0.086 for lambda. Don't forget the negative sign. Now, what else can we do here to simplify this equation? What's the first and simplest thing we can do to simplify this equation?
Solve for E to negative
I think the simplest thing to do is to notice that there's an A naught term on both sides, which means that we can basically cancel the A naught from both sides. What we're really doing is we're dividing both sides by A naught. If you divide both sides by A naught, then it cancels from both sides. Now this is going to happen on most of these problems, because usually they're not giving you the level of activity, they're just giving you the ratio of the activity. And if you're given the ratio and you make this type of substitution, you're always going to be able to cancel out the actual level. So this is pretty common on this type of problem. All right, now we have some more difficult algebra. We need to solve for t, but the t is imprisoned up here in the exponent. So we need to remember from algebra, how do you get variables out of exponents? There's a trick for getting variables out of exponents.
Do the ln.
You take the log, that's right. Any log would work, but in this case the natural log is the best. let's actually review a little bit of the math there. What is the log of x to the y power? How can we rewrite that?
Isn't it 10 to the x equals 1?
Now, it looks like you're just trying to interpret this log over here. But the point is that the nice thing about logs is they pull down exponents. The nice thing about logs is they pull down exponents. It doesn't matter whether this is base 10 or a natural log. This works with any type of log. Any type of log. Maybe I should have stuck with ln though, because I guess that's really what we're going to be using. So why overcomplicate things? This would work for any log, but let's focus on natural logs. So like any other log, a natural log brings down the exponent. Well, this is very handy if you need to get a variable out of an exponent. So let's take the log of both sides here. You can take the log of the left if you take the log of the right. And let's use our calculator to find the log of a third.
So that's negative 1.09. So negative 1.1.
Negative 1.1. And how does this right hand simplify? Well, we get to bring the exponent down. We can't forget to bring down the negative sign. But we still have to take the natural log of e. Just like over here, we'd have the natural log of x.
And this is the ln of e 1.
That's right. You can check that on your calculator, but the natural log of e is 1, because they're inverse operations of each other. Natural log is the inverse of the e operation. I don't know if we actually have an e. Yeah, this calculator might not really have an e. It has EEX, but it doesn't have an e. But if you try this calculator, natural log of e is 1. Okay. Why don't we just put that in our cheat sheet, because that'll be important for solving problems. The natural log of e is 1, because they're inverse functions of each other.
So actually negative 1.1 divided by negative 0.086.
Mm-hmm.
T equals 12.8 days.
That's right. That's good that you remembered the units. Since lambda was in days, t will be in days over here. You can see on these problems you have to be careful with the signs. There's always going to be some negative signs here. And now we figured out what this horizontal intercept is. It's probably a good idea to try to draw these graphs for these problems so you can see conceptually what you're doing. We started with maximum radioactivity, and we're waiting to see how long it takes for the radioactivity to fall to 1/3 of what it started at. And we got that that would be 12.8 days. So there were some important math tricks that you want to have prominently in your notes here. First of all, a lot of these problems don't give you the levels, they give you the ratios. And a good way to deal with that is first write an equation involving the ratios, then we substitute, and since it's a ratio, the variables for the levels will cancel out. So we have to look to do that. And then we still have more problems because we have to get the variable t out of the exponent. Well, we can use the natural log trick to get it out of the exponent. We have to also remember that log of e is 1. So there's a bunch of math issues that come up when we're dealing with these equations. And like I say, you're pretty sure to see this on the test. This is a very standard type of problem. Or a relative of this that we'll get to in a second, anyway. By the way, this is very practical information. Suppose that you have, let's see, iodine 131. Yeah, so iodine, according to the textbook, iodine 131 was one of the radioactive byproducts that was produced in the Chernobyl accident. I don't know if you remember, you haven't heard of Chernobyl? All right, that was from when I was a kid, not when you were a kid. So Chernobyl was a Soviet Union nuclear facility that basically blew up in the 80s. It melted down or whatever they say. It was a huge disaster that killed a bunch of people and blasted a whole big area. And anyway, one of the things that made it so dangerous is, I guess, it blasted this iodine 131 all over the place. Well, then you want to know, how soon will things be safe? When will the radioactivity get down to a safe level? Well, this is the exact type of calculation you need to do. How long will it take for this radioactivity to fall to 1/3 or 1/millionth of the previous level, or whatever it takes to get back to what's considered safe? So there would be a good chance that if you saw a question on the exam, it would be phrased in those kind of real-world terms. we did this problem for how long will it take the radioactivity to fall to 1/3 of its previous level, how long would it take the amount of iodine to fall to 1/3 of its original level? How long would it take the amount of iodine-131 to fall to 1/3 of its original level?
Wouldn't it be the same?
Because that would just involve n's, but the equation for the n's are the same as the equations for the a's. You would simply rewrite this equation, this graph, in terms of the n's. So we would solve equations about the amount of material exactly the same way as a problem about the activity of the material.